today we are going to start advanced reaction engineering. So, in this class we will discuss about the effect of pressure drop on reactor designs, that is packed bed reactor, that already have discussed the preliminary or basics equations, differential equations, how to derive that, that already have discussed. So, uh, in the pressure drop or the packed bed reactor. So, how conversions will affect with the bed height or catalyst weight and pressures also at the same times, that will affect if we change the catalyst weight, means how the pressures is a function of catalyst weight. So, if we take a higher amount of catalyst in a bed, so then gradually the pressures that will be developed or pressure drops would be there inside of the beds. So, once we changes, means always if we conduct any reactions in a packed bed reactors, we always expect that if we put catalyst quantity more and more, so then conversions will be higher. So, conversion as a function of weight of the catalyst, that is expected. So, but at the any amount of the catalyst we cannot put inside of the reactor. So, if we charge more and more catalyst, then pressure drop also will be developed there, and then that pressures that will affect the overall efficiency or the catalyst means reactor efficiency of that, means in terms of conversion yield, selectivity or rates, that would affect. So, here is the packed bed reactor that already have discussed. So, here let us say this is the reactions and this is the design equations and this is the reactors already we have discussed, and these are the two equations, means differential form of equation, these equations, one equation. So, this equation, so dx by dw means as a conversions as a function of catalyst weight, that already I have discussed in isothermal conditions, and then we have derived the argon equation, means we have started with the argon equations. So, we have discussed each and every elements in this particular reaction. So, this is the argon equations I said. So, in the means these are the two equations. So, these equations and these equations would be useful, equation A and equations 1. So, that would be useful for study of the pressure drop in a packed bed reactor. So, here let us say the density of the gas, we means here we will consider gas and solid reactions, means gas is the reactant and catalyst is the solid particles. Let us say if we increase the temperature of that gases, then the density or other parameter will change. So, means in case of the gaseous system, so density of that gas, that would directly proportional to that particular density of that component or that gaseous mixtures will affect with temperatures as well as pressures also. So, how they are related? So, let us say if we have a systems, we want to calculate the pressure drop at the catalytic bed. So, first we have to consider the systems as a reactor operated at steady states, and then let us say m dot, that is the we are expressing m dot, that is the kg per second, that is the reactant, that is the mass flow of rate of the reactant in the reactor at any points, and m 0 that is the entering mass flow rate, means this is the reactor. So, here this is mass entering, and inside of that any locations if we collect that mass, so that would be m dots. That way we changes inside of the bed, if it is there is a changes of temperature or pressure inside of the bed. So, accordingly the mass flow rate inside of the bed also would be different, means the gas is, means the density of the gas directly dependent on the temperature and pressure of the system. So, therefore, mass flow rate also inside of the bed would be different. So, if we change the temperature and pressure. So, if we consider m 0, that is the entering mass flow rate, and m dot is the at any points inside of the reactor the mass flow rate in terms of kg per second. So, then at steady state we consider that this equals to m dot equals to m dot 0 at steady state. So, m dot equals to kg per second we said. So, if we multiply it with the volumetric flow rates V, that is the dmq per second. Okay. So, density equals to kg per dmq, that units. Okay. Rho is this. So, if we multiply this, then mass flow rate will come kg per second. So, here left hand side and right hand side depending upon that. So, we are multiplying with V naught and here V. So, now this is the balance equation, material balance equations means entering a mass and inside of a reactor at any point inside of the bed should be the same. So, at once it is the steady state operation. So, here's volumetric flow rate. In our earlier study we have discussed that volumetric flow rate V volumetric flow rate of the feed, that gaseous feed as a function of temperature and pressures, fraction volume changes and conversions, how they are related. So, here's V we can substitute here in this equations, and then we can rearrange V we are substituting here in this equation. So, then density we are taking at any point inside of the reactor the gas density. So, in terms of this we are getting. So, or simplifying these equations we can get rho equals to rho 0 P by P naught, F T naught by F T and T naught by T. So, here's F T naught by F T that we have discussed in our previous class also, F T by F T naught, that is how they are related. So, we here means derivations is there, already we have discussed in our previous class also. So, here we can write F T by F T naught equals to 1 plus epsilon into x. So, fractional volume change and how they are related, molar flow rates and total molar flow rates, how they are related. So, now equation 3 we can get, and now in argon equations we are substituting the density. In argon equations you can see there is the density component is there. Okay. So, the density we are substituting in these equations. So, here if we substitute in these equations the density, so then the equations we can write, or final equations will get this. So, once we substituting this density in equation 1, there you will get this. So, here in this equation we are expressing in terms of minus beta 0 P 0 by P, F T by F T naught, T by T naught. This is against reconsidering or changing this equation into this. Here these are the terms except minus, these are the terms we are considering as a beta 0. Okay. So, means except minus P naught by P, F T by F T naught, T by T naught. So, rest of the terms we are taking, this is the beta 0, that is the pressure parameter usually say in this type of, means we consider it as a pressure parameter, or so, this part then equation should be much more simple. Okay. So, beta naught P 0 by P, F T by F T naught, T by T. Okay. So, here dP by dz equals to this, means equations 4 we are getting. So, now we said that there is a relationship in between catalyst height, catalyst bed height and catalyst weight. So, how they are? So, that we will discuss here. Z is the reactor bed length and W is the weight of the catalyst. So, W kg of catalyst, let us say, and bed length is Z. Okay. So, how they are related? So, here W is the weight of the catalyst equals to here density of the solid catalyst. If we multiply it with the volume, solid volume, so then volume of the solids and density of the catalyst we are multiplying with this. So, this terms is the volume and this term is the density. If you are multiplying, then the weight of the catalyst will get. So, 1 minus phi is the solid volumes, AC is the cross sections area you can see here, and Z is the length. So, let us say Z length of the catalyst bed is there. So, if we multiplied AC into Z, then that would give, means a volume 1 minus phi, if we multiply, then the solid volumes will get, solid volumes multiplied with the catalyst density, solid density, density of the solid catalyst we multiply. So, then we will get the weight of the total weight of the catalyst in that. So, here Z and W there is some relationship. If we convert that into in terms of differential forms, dW equals to AC Z, that would be in terms of delta Z dz and rho C and into 1 minus phi. So, these equations in differential form we can write, this is for the total system, total weight, total length of that bed, and this is differential form, means any small sections or elements that we can write this way. So, now equations 5 is coming in terms of dW by dz. Now, in equations 4 we have dP by dz, here dz whatever we have, that we are substituting in terms of or rewriting this in terms of dW. So, equations means 6 we are getting dp by dw, means either we can write in terms of dp by dz or dw. So, here we are changing that dp by dw. So, that equals to simple equation this. So, these are the terms will come. Okay. So, equation 6 will come, it is much more simple or simplified equation. Again we will do further simplification. So, dp by dw equals to, means here this term is was there. Okay. So, these terms how we can change, see here the equations. So, here a alpha one more parameter, that is alpha we are taking here. So, alpha equals to 2 beta 0 here multiplied with the 2 top and bottom. So, and then this parts. Okay. So, here you see you have divided with 2. So, here we get alpha equals to, we are considering this part is alpha, and alpha in terms of means alpha directly proportional to the beta 0, beta 0 that is the pressure parameter or alpha, both are same directly proportional. So, some factor is there. So, here dp by dw will get and these equations here p by p naught, that is the y we are considering. Okay. Matlab whatever the equations we have argon equations, one by one step we are going and simplifying and that equations for our analysis. Then d p by p by p naught, p naught is the bed initial pressures. Here pressure is pressure p naught, let us say we have started with 10 bar pressure and p is the pressure at any locations pressures. Okay. So, any points. So, this is the ratio, y is the ratio of the pressure p by p naught. So, that is the y. So, that we can assuming it, let this equals to this. So, now here's in the left hand side differential forms, if you dp equals to dy into dp 0 would be there. So, this way we can replace in terms of dy also here. Okay. So, replaced here. So, that will get this equation, equation 8 in terms of dy by dw minus y is the pressure terms. Okay, pressure ratio alpha by 2 y. Okay. So, here also p by p naught is there. So, therefore, here y is also coming. So, then the equation 8 is useful for multiple reactions if there is any pressure drop in the reactors or the reactors we are using. So, now we are Ft by Ft naught equals to this, we have also derived in that also we are substituting here. So, then equations 9 we are getting. So, equation 9 is the dy by dw, that is the we can say. So, this is the y is the pressure terms I said p by p naught. Okay. So, here pressure term is there. So, pressure that is the fractional pressures you can say, or dy the pressure that is the changes inside of the bed. So, here if we know the temperatures at different locations, fractional volume change for that particular reactions, and alpha value how we will get. So, here 2 beta 0 by AC rho c 1 minus phi into p 0 or p naught is there. So, if no alpha value beta value first we have to calculate, we have to put it here, and beta once beta 0 value we know, then alpha value we will know, once alpha value know, then we can put it here. Okay. So, then these differential equations is in the form of means this is the argon equation in the form of differential, that is the pressure of that these equations 9s we can use for changes of the pressures along the length of the catalyst beds, that we can means find out using these equations. We have to solve that, maybe analytically or numerically we can solve these differential equations. So, here's two cases we are considering, let us say E equals to 0, there is no volume changes as or there is no volumetric flow rate changes in the reactions. So, in that case if E equals to maybe negative, E equals to epsilon may be positive, that depending upon that. If E equals to 0 means there is no changes of volumes during reactions, or there is no volumetric flow rate changes. This is from the reaction stoichiometry, from reactions point of view. So, if it is 0 then so there is no pressure drops. If this means E epsilon that is the negative, then there will be pressure drop that would be less than E 0, means that is the, if we consider there is a no volume changes, if it is negative then there will be a pressure drop that is the less. Okay. If positive then also there will be a pressure drop that would be greater than from E equal to 0. At E equals to 0 we are expecting there is no means volumetric flow rate changes during reactions. So, as compared to that, either it may be positive or it may be negatives depending upon the reactions. So, this is also would affect the overall, means this part we are considering here, means fractional volume changes, that also is very important, that parameters, means if it is depending upon the for a particular reaction, that is standard. So, that is the fixed for depending upon the stoichiometry of the reaction. So, if it is positive and if it is negative or if it is 0, then how that would direct. So, if it is 0, then we can directly eliminate these components, that equation should be much more simple. Okay. So, here means in our from now today we have derived these equations, these differential equations from the Argand equations, and from the material balance equation or design equations of the packed bed reactors we have derived these equations. So, these are the two differential form of equations. This equation in our earlier class we have derived this one, and today we have derived this equation. These two equations we have. So, these two equations simultaneously we have to solve. Okay. So, these differential equations we have to solve simultaneously, then we can get from these equations A will get conversions and weight as a parameters. Okay. These are the different value. If we change catalyst weight, then corresponding conversions will get. Okay. So, this value will get from these equations, and from these equations we get pressure and W pressure. So, what would be the pressures at different, if we change the catalyst quantity. So, that will get, these are the value will get. So, there are so many numerical integrations or software packages available, so that we can use to solve this differential equation to this equation, and then simple numerical value that would come. So, in the form of tables. So, if we put all right hand side parameters during this integrations, and here also, means all these components are known, only conversions we can fluctuate or we can vary from, or catalyst weight vary. So, then conversion accordingly that will change, and then conversions and catalyst weight, these curves will get from these equations. Here I am not saying how, what would be the nature of the curve. So, that we will discuss later. So, just these plots x versus w will get, x versus w will get, and here p versus w will get, means how pressure changes with the catalyst weight. So, that we will discuss. So, what would be the natures of that. Okay. So, we have studied means we have developed differential equations, means y, here y is the p by p naught. So, y if we get means multiplied with p naught. So, then pressures at any locations, that is equals to pressures of this. Okay. So, in the bed pressure at different location, that we can get. So, these are the two equations we have to solve, and simultaneously by different techniques. So, these are things we have studied today. Okay. So, thank you very much. So, today is up to this. So, in our next class we will discuss by changing different parameters in these two equations, means by considering various assumptions and different case to case. I said here so in the packed bed I said, so catalyst we can take larger size particles, medium size particles, smaller size particles. So, this is the diameter of the particle. So, if we changes dp 3, dp 2, dp 1, so smaller particles. So, if we place these one by one particles different diameter of the particles, so that also will change the conversions as well as pressures inside of the beds. So, same quantity, means let us say W equal to 10 kg of catalyst you have charged inside of the beds. So, catalyst quantity remain the same, but catalyst particle size would be different. So, smaller particle size we can take 10 kg, or we can take larger size of the particles 10 kg. So, both the total quantity of the catalyst remain the same, but when catalyst particle size we are changing. So, then how that would affect overall pressures as well as conversions, concentrations, rate. So, various parameters we can evaluate. Okay. So, these are the things we will discuss. So, what would be the optimum catalyst particle diameters, that we should know. Otherwise means any diameter, whenever we are going to design a packed bed reactors, any diameter of catalyst particle size we cannot take, since this is the pressure effect will be developed. So, at the same time, we also study the effect of catalyst particles. So, since it is the gas solid reactions, so here gas particles, gas molecules will come, that would enter or passes through this, is there is this molecules does not take part in the reactions, but the molecules interact with the catalyst particles. Catalyst, we said that let us say this is the catalyst, these are the active sites of the catalyst, and catalyst if it is solid catalyst, inside of the catalyst there is so many pores are available. So, these pores, let us say these are the pores available. So, in the pores catalyst active sites are available. So, reactant molecules may pass over theirs and interact with the catalyst active sites, and then that would give corresponding product. Okay. So, inside of the pore is there. So, depending upon smaller diameter particles, larger diameter particles, the availability of that active sites will also vary. So, means external internal diffusions, means this is called internal diffusion. So, if we change smaller particle, larger particles, the reactant molecules also diffused through that reactor or through these particle catalyst particles, and depending upon that there would be reactions, means interactions with the reactant molecules to the catalyst active sites, that would be different or that would vary. Once that would vary, means that catalyst means the product conversions, yield, selectivity, everything will change also. So, here we cannot either increase the catalyst particle diameter any size we cannot consider. So, what would be the optimum, means these are the things we have to means keep in mind. So, whenever we are going to design a catalyst for a particular system. So, these are the things always we have to keep in mind, means here's and here's in optimum diameter of that particles that you have to choose or you have to select, means once reaction is fixed, catalyst is fixed, reactor is fixed, then catalyst diameters that also we have to mention whenever we will purchase or will install for that particular reactor. So, then that should be 10 millimeter diameter of each particle should be there, that is in the form of spherical. Then with that we can optimize the pressure drop inside of the reactor, or at the same time we can get more conversions, more and more reactants will get converted into the corresponding product, means diffusional effect, internal diffusion we can eliminate. Okay. So, that also we have to keep in mind. So, that part we will discuss in our next class or next lectures. Okay. So, these are things you should read. I hope you understand it. So, thank you very much. So, today is up to this, next day we will discuss the different analytical solutions of this particular differential equations. Thank you.